All right, we are in section 7.1. We'll do the warm-up. And the thing I want you to keep in mind is section 7.1, there's a lot of fancy words. There's working backward, inverse function. This is just, all of this, it just means you're solving for x. So this section, you're just going to get a lot of practice at solving for x. So if we start with our warm-up, and we have converting from Fahrenheit to Celsius. To convert from Fahrenheit to Celsius, you can do C of x, where x is degrees Fahrenheit, is x minus 32 times 5 over 9. I subtract 32, multiply result by 5, divide by 9. So now I can do, let's say, C of 20 equals 20 minus 32 times 5 over 9, which is negative 60 over 9. That's negative 12 times 5, negative 60 over 9. I can do C of 112 is 112 minus 32 times 5 over 9. 112 is 80 times 5 over 9. I should have picked a simpler number. That's just about 9. That's approximately 45 Celsius. All right, so now let's say if the temperature is 15 degrees Celsius, what is the temperature in degrees Fahrenheit? That just means take your function, set it equal to 15, and solve for x. That's pretty much all we're going to be doing in this section, solving for x. So in this case, you can multiply by 9 over 5. That's 3. So 27 equals x minus 32. So x equals 27 plus 32, which is 59. So 59 degrees Fahrenheit. Now, if we want to go one step further, we could actually write the inverse function. So if my function C of x is x minus 32 times 5 over 9, then my function f of z, where z is degrees Celsius, would be 9 over 5 z plus 32. But again, what we're doing here is we're setting up an equation and solving for x. And that pretty much covers the warm-up. Just really briefly, because it's also in the warm-up, fractional powers and roots. So x to the 1/2 is a square root of x. X to the 1/3 is the third root of x. X to the 7/5 is x to the 7th in the 5th root. And so it helps to be able to go back and forth between these, and undoing a root. You undo a root by the reciprocal power. Reciprocal power. What I mean by that is if I have x squared equals 16, then x equals the square root of 16, or 16 to the 1/2, which is 4. if I have x to the 2/7 equals 25, then x equals 25 to the 7/2, because 7/2 is the reciprocal of 2/7, which is 5 to the 7th, which is a big number. I don't want to do that. If I have x to the 4/3 is I don't know, 256, then x is 256 to the 3/4, which is usually, if you're doing it in your head, it's easier to do the 4th root first. Cubed, which is 4 cubed, which is 64. All right, that's a little review of fractional roots. So now moving on. I'm just looking through the notebook. Okay, we're just going to start chugging through lots of different equations. So if I have, let's see, 3 to the x equals 81, then I'm solving for x. How do you get rid of an exponential? You do the log of that same base, and there's a lot of ways to think about it. You can take the log base 3 of 3 to the x equals log base 3 of 81. And so if you want to just do it quickly, if it's 3 to the x and log base 3, you cancel and you just get x. And log base 3 of 81 is the power that goes on 3 to get 81, which is 4. You could also, if you want to use your log rules, you can notice that an exponent can be pulled down in front as a multiplication, and you can notice that the log base 3 of 3 is always 1. That's the other way to get x. Or you could also just take this and write it as the statement x is the power that goes on 3 to get 81, and that gets us to here as well. So x is 4. Other ones, I could do the cube root of x equals 4. And so I can rewrite that as x to the 1/3 equals 4. So to undo that root, I have to raise both sides to the reciprocal, which is just the cubed. So x is 64. I could do e to the x equals 7. And since it's my base e, I can do natural log of e to the x equals natural log of 7, and the natural log and the e cancel, and I get x equals natural log of 7. That is the answer because this is a number. It just doesn't look like a decimal, but it is a number. I could have the 4th root of x equals 3. That's a 4th root, so it belongs up there. So that's x to the 1/4 equals 3. Raise both sides to the reciprocal, which is the number 4, and x equals 81. I'm just doing a bunch of these. You can just watch me go through them, or when I write it down, you can pause and try to do it yourself. I could have x to the 7th equals 128. How do I get rid of the 7th? I raise it to the 1/7. I can grab my calculator, or I happen to know that that is the number 2, so x equals 2. Any others? These are all pretty basic ones. I could do the 5th root of x equals -8, which is okay because it's a 5th root, it's an odd root, so negative makes sense. So x would be -8 to the reciprocal of 1/5, which is 5. I don't know what that number is. That's to the 5th, that's a big number. I don't know what that is. It's 3, 2, 7, 6, 8. With the negative, because that's a negative. All right, and maybe I have 5 to the x equals 68. How do I solve that? Well, I see it's a log base, or it's an exponential base 5, so I can just take log base 5 of both sides. Those cancel, and I get x equals log base 5 of 68. That is the answer, because that's a number, even though it doesn't look like a decimal. What number is it close to? What decimal is it close to? Well, that's hard to say because my calculator doesn't do logs of any base other than 10 and the natural log. And so for this, we'll use another log rule, which is you can always rewrite. Let's try that again. Rewrite log base b of x as a natural log of x over the natural log of b. Or you can write it as log base 10 of x over log base 10 of b. You can really write it as any log. You can write it as log base a of x over log base a of b, but one of these is the ones that's useful. That's base e and that's base 10. So I had x is log base 5 of 68. So I can rewrite that as natural log of what goes in there, 68, over the natural log of the base. And now I can use my calculator to figure that out and get an approximate decimal. It's approximately 2.62. So this rule again says if I have a log base b of any number, I can rewrite it as a natural log of the number divided by natural log of the base. I'll do a couple more of those just so you can see. So if I have log base 3 of 7, I can write that as natural log of 7 over natural log of 3, which now I can do in my calculator. If I have log base 50 of 2, I can write that as natural log of 2 over natural log of 50. I could also write it as log base 2, log base 10 of 2 over log base 10 of 50 if I wanted to. This is useful only insofar as now my calculator can give me a decimal approximation. But I will always accept an answer written in any base. All right. In general, solving b to the x equals c. This is page 163. They call it the inverse method. I don't call it the inverse method. I'd say using logs or rewriting it as a log. So there's, like I said, there's 3 ways to do it. The first way, which I like, is just reading this as a sentence. X is the power that goes on b to get c. And if I need to write that as a natural log, I can write it as natural log of c over the natural log of b. I could also say I have a b to the x, so I'll take a log base b of both sides, which we can do because log is an inverse function. So I can run this through and I'm guaranteed that if these things are equal, then these things are equal. And I recognize when I have something raised to a power, I can write it as as a product in front, and then I recognize log base b of b is always 1. And I get that answer. Or this is the exact same, but I just kind of skipped that step because I remember when I have log base b of b to the x, I can cancel those and it's just x. That's fine. If you just remember log base b of b to the x, you cancel it and you get x, then you're fine. That's our summary. I can solve logarithmic functions if I know that x equals, no, that's not what I wanted. Sorry. If I know that log base 3 of x equals 24, I say, oh, I have a log base 3 of x equals 24. So again, there's at least a couple ways to do it. I'll just do two. The first way is to say, oh, okay, 24 is the power. 24 is the power that goes on 3 to get x. So I have to figure out what that number is, which is very big, and I'm not going to do that. Or I can say I have a log base 3, and since logs and exponentials are inverses, I can do 3 to the log base 3 of x equals 3 to 24, and those cancel, leaving me with x equals 3 to the 24. Couple ways to solve log equations. All right, let's do some more. So far, you've only been seeing things like x by itself, but it doesn't have to be that way. I could say something like 343 equals 7 to the x plus 2. And I say, okay, I have a 7 there. Let me just treat this like a term, just like a whole term, and not worry about it. And so since it's a 7, I want log base 7 of 343. Should be log base 7 of 7 to the x plus 2. Log base 7 of 7 cancels, leaving me with x plus 2 by itself. And I happen to know that log base 3 of 343 is equal to the number 3. And now it's linear. And then I just subtract 2 from both sides, and x equals 1. Again, remember back when I was talking about logs, I say logs turn things from exponentials into linear. I took a log of both sides, and all of a sudden I have a linear equation here. I could have something like 173 is equal to e to the 3x minus 4. I see I have an exponential here with a natural base, so I'll take natural log of both sides. And when I have a natural log of an exponential, they cancel. That is a number. The decimal approximation is approximately 5.15, but I'm okay just leaving it like that. Log of 173 is equal to 3x minus 4. This is now a linear equation. A number equals 3 times x minus 4. Went from exponential with the log, I made it linear. So natural log of 173 plus 4 equals 3x. So x equals natural log of 173 plus 4 divided by 3. And that's good. I'm done. I don't need to know exactly what that decimal approximation is, because that is the number that makes this statement true. I can do it the other way. If I have logs, let's say I have log base 2 of 5x plus 8 equals 512. Oh, I have a log base 2 there, so I'm going to raise everything on top of 2. This was a really bad example because that number is way bigger than I want it to be. Scratch that out. Start over. That's bigger than the number of atoms in the universe, so let's not follow that any further. How about this? Log base 2 of 5x plus 8. equals 7. That feels better. Or even 9. That's the number I wanted, 9. Okay, so now I'm going to say raise both on top of the exponent. Oh, what I did just there is kind of sneaky. I was like, I want them to be exponents, so I just wrote 2 in the base. 2 log 2 cancels, so I get 5x plus 8 equals 2 to the 9th. 2 to the 9th is the number 512, which is what I was going for in the first place. And now this is just a nice linear equation. 512 minus 8, which is 506. Nope, 504. And so x is 100. Well, it's 504 divided by 5, which is just shy of 101, 100.8. There we go. So seeing a bunch of terms inside of a log. Let's call it m, some number. You just treat the terms all together until you get rid of the log. If it's log base b, I raise both things on top of the base b, and those cancel. And b to the m is some number. And now I can solve for that. All right, that's a lot of logs and a lot of exponentials. There are some other functions. I'm going to throw a super easy one at you that you've done many times. Let's say that 2x minus 5 equals 12. That's super simple, and you've done that many times. But it's the same process as with logs and exponentials. You just are using slightly different mathematical tools. So let's say I have x minus 3 to the 7 halves equals 13. I'm going to need my calculator for this, but that's okay. And I want to solve this. Well, the first thing to do is think of these as terms, and to get rid of the 7 halves, we need to raise both sides to the reciprocal, which is 2/7. And now I just have x equals 13 to the 2/7 plus 3, which is some number, and I will look that up. Approximately 5.08. Okay, so most of this section is just solving for x, even though they throw some fancy terms like working backward or using an inverse function, but it's just solving for x. And now the only tricky part here is what happens when solving for x gives you a false answer. All right, so that can happen when you start with a function. Maybe your function is p of x equals the square root of x minus 3. So I could solve p of x equals 5. And that just means 5 equals the square root of x minus 3. So 25. So if you if you square both sides, you get rid of the root. 25 equals x minus 3, so x equals 28. That's no problem. But what if I said solve p of x equals -5, and you just chugged through the algebra without thinking about things? Those cancel. -5 squared is 25. X minus 3. So that means x equals 28. But does it really? Does that work? Let's try it. P of 28 equals the square root of 28 minus 3. And that's equal to +5. +5 and -5 are not the same number. So this is what I call a false answer. What the workbook calls an extraneous solution. I'm going to do one more example and then I'll talk about how you can be alert to extraneous solutions or to false answers. I think I have just enough space on this page. So let's say that f of x equals the square root of 2x plus 1. And I want to solve f of x equals -3. The way you catch a possible false answer is you ask, could this ever be true? Could it ever be that the square root of something gives you a negative number? Square roots cannot produce negatives, so there is no answer. That's how I would recommend catching yourself before you find a false answer, is to ask yourself, could I even get an answer from this equation? There's another way to catch it, and either way works fine. The other way is to actually go through the process, go through the steps. So if I want to unwind the square root, I square both sides, and I get -3 squared, which is 9, is 2x plus 1. So 8 is 2x, so x is 4. And here's where I check. So the other way to do it is to check the answer. And so I plug 4 in to the square root. 2 times 4 plus 1, which is the square root of 9, which is 3. And since 3 and -3 are not the same, x equals 4 is a false answer. So it's possible when you're solving for x, you find a false answer. And the best way to avoid it is just to ask yourself before you even start, could I actually find an x value that would give me what I have here on the left side? Here's another example. Solve -7 equals the natural log of x plus 2. Nope, that's okay. Never mind. Not that one. How about we do this instead? Solve -3 equals e to the x minus 1. There we go. E to the x, e to any power, any base to any power is always positive. So this is not possible. There is no solution. There's no x value. There's no exponent that could possibly get a negative number out of an exponential function. And if I go through my process, I want to do log of -3 equals log of e to the x minus 1. And hopefully you recognize, oh, you can't do logs of negative numbers. So again, that's not possible. At every point here, you should be recognizing this is not possible, this is not possible, this is not possible. Your danger is if you just leave it like this and you don't think about whether this is possible or not, and you think, okay, that's a number, I'm not going to simplify it. Well, this is not a number, and so this is a false solution. End of video.